In the last video, we discussed how we define the eigenproblem, how we get the eigenvalues and the eigenvectors, and we did a simple 2x2 example, which came from a stress tensor problem. Here we're going to look at a bit more ambitious problem, where we have a 4x4 matrix that we want to find the eigenvalues and eigenvectors of. First thing you'll notice, it is not symmetric, so you can see the off-diagonal elements are not symmetric around the diagonal. So, not sure quite what that means yet, what the impact is for this problem, but let's follow through and just keep that in mind as we go. So, we form the determinant of a minus lambda I, and we set that equal to 0. Once again, that's because we have a homogeneous system. We want non-trivial solutions. The only way to have a non-trivial solution is if the coefficient matrix A minus lambda I is not invertible, so that it is singular and has rank less than capital N, and so on. So we want the determinant of A minus lambda I to be equal to 0. So we start with the original matrix A, and we subtract off lambda from the main diagonal terms, set that determinant equal to 0. Now the first thing you'll notice here is because it's 4x4, we can't use our usual cross multiplication technique for getting the determinant that we do for 2x2 and 3x3. Instead, we're going to have to use a cofactor expansion. This was discussed in Chapter 1. And the easiest way to apply the cofactor expansion is to find a row or column, ideally with as many zeros as possible. And you'll notice that the second column has all zeros except for one element. So if we take a cofactor expansion around this location right here, then it'll make our lives a bit easier. All right, so if you remember how the cofactor expansion goes, you take out the corresponding row and column, you collapse it down to, in this case, a 3x3 matrix, and you have the determinant of that, that's the minor, times 2 minus lambda. All the others just have 0 times their respective minors, which of course are all 0. So we end up with 2 minus lambda times the determinant of the 3x3 matrix that's left. That's the minor. So now we can do our cross multiplication. So we have 2 minus lambda times the 3x3 matrix determinant, that's the minor, that's left when we take out the corresponding row and column. So now for this 3x3 matrix, we can indeed use our cross multiplication technique for determining the determinant. So we have 2 minus lambda, and then in square brackets, we're going to have the determinant of the 3x3 minor. So it's minus lambda times 2 minus lambda times minus lambda, plus 1 times 1 times 1, plus 1 times minus 1, and that's these first three terms here, and then minus 1 times 2 minus lambda times 1, it's right here, minus 1 times minus lambda here, and then minus lambda times 1 times minus 1, which is here. Okay, now normally the temptation would be to multiply this all out and simplify it down to, in this case, a fourth order characteristic polynomial. Instead, what we want to do is look for common factors and keep them out as much as possible, because we'd have to use some sort of mathematical software in order to factor a fourth order polynomial. So instead, if we can identify common factors, that'll make our lives much easier. So we already have a 2 minus lambda times everything else. Are there any common factors in the square brackets here? Well, you can see here we have 1 plus 1 minus 2, so those all cancel. Here's a plus lambda, minus lambda, so that's minus 1 lambda. So if we can simplify this down to this, you'll notice that we have a lambda in both terms that we can factor out. So factoring that out, we have a lambda times lambda minus 2 times then a second order polynomial left. Now we're happy because we can use the quadratic formula, we can factor it by inspection, and in this case it's just lambda minus 1 squared. So we have lambda minus 2, and then this results in lambda minus 1 squared. All right, so just keep that in mind. Always look for those common factors when they're available. Okay, so then we have our eigenvalues, 0, minus 2, and minus 1 with multiplicity 2, because it occurs twice. So 0, 1, 1, and 2. So, all right, second road sign, we have a non-symmetric matrix. Turns out we do have repeated eigenvalues. Let's see what difference that makes. First, let's go ahead and get the eigenvectors that correspond to the distinct eigenvalues. That should work out just like before, and then we'll see what happens with the repeated eigenvalue. For lambda being 0, subtract 0 off the main diagonal elements. You get our system of equations that we want to solve for the eigenvector u1. Now, again, we're always looking for equations that are in common or linear combinations of other equations. Here, it's not so obvious that any of these are the same. However, if you look closely, you'll notice that if you add the third equation and the fourth equation, you'll get the first equation. So the first equation is just a linear combination of the second and third, and therefore you lose an equation. If you don't see that, that's fine. Just do Gauss elimination. Elimination does not change the solution of the system, it just simplifies it down. So, recognizing that the first equation is redundant, we have 3 equations for our 4 unknowns. So we lose an equation, so we have one arbitrary variable. I'm going to say u1 is just a constant c1, some arbitrary constant. And then if I look at the last of these equations, if I know u1, I can get u3. That has to be the same, so u3 is c1. Once I know u1 and u3, I can get u4 from the second equation, and u4 would then have to be minus c1. And then finally u2, once I know u1 and u4, I can solve for u2 as just c1. So my eigenvector that corresponds to the eigenvalue 0 is just an arbitrary constant c1 times 1, 1, 1, minus 1. Once again, we'll generally not include the arbitrary constant because it's assumed, but I've included it here just for clarity. So 1, 1, 1, minus 1, or times any arbitrary constant gives you the same eigenvector. Okay, so this is a regular eigenvector, came through the regular eigenvector procedure. Let's try lambda is equal to, which is also a distinct eigenvalue. Subtract off 2 from the main diagonal terms in A. We now have a new system of equations for u4. In this case, you can easily see that the second and third equations are exactly the same. So we really only have 3 equations for our 4 unknowns. And once again, I want to solve these. So I now have 3 equations for my 4 unknowns. And we can solve this in any fashion that we want. Here I've used Gauss elimination. That's not necessary, but just to simplify this down, I've used Gauss elimination to make this even easier. So you can now see through back substitution, u4 has to be 0. If u4 is 0, then u3 has to be 0. If u3 and u4 are 0, then u1 also has to be 0. You'll notice u2 does not appear anywhere in our equations. So whereas u1, u3, u4 all have to be 0, u2 can be completely arbitrary because it's multiplied by 0. So you have to be careful not to get too excited. You see these zeros popping up, and so you're tempted to just say u2 has to be 0. But in fact, it could be completely arbitrary. So our u4 eigenvector is an arbitrary constant c4 times 0, 1, 0, 0. Again, the 1 is in the u2 slot so that you can have an arbitrary value there. Okay, so that's our second eigenvector. Again, it's a regular eigenvector obtained through the regular routine. Now let's tackle the new piece, which we haven't seen yet, and that is where we have a repeated eigenvalue, in this case 1. It's repeated twice, so we're hoping to get 2 eigenvectors out of this one eigenvalue of multiplicity 2. So subtract off 1 from the main diagonal. I'm going to remind myself that I'm looking for two eigenvectors here by calling this u2, 3. And then we go through the usual procedure, and let's just see what happens. So you'll notice that the first equation, the third equation, and in fact the fourth equation are all the same. So I actually lose two equations. So now we have two equations for four unknowns. So for unknowns, two equations, that means two of our variables can be arbitrary. So I'm going to select u1 and say that's c2, and u2 and say that's c3. So u1 is c2, u2 is c3. And if we go back and look at these two equations, then given those arbitrary constants, we can see that u4 then has to be c2 minus c3, and u3 is c2 minus u4, but if u4 is c2 minus c3, then that simplifies down to c3. So that gives us our general expression for an eigenvector, c2, c3, c3, c2 minus c3. Now remember, these constants are completely arbitrary. So I can choose two separate pairs of c2, c3 constants to get my two eigenvectors, u2 and u3. The only requirement is I want them to be linearly independent. I don't want the two vectors actually to be the same and just one is a constant multiple of the other. I want them to be two linearly independent eigenvectors. Other than that, I can choose whatever I want. So I choose c2 to be 1 and c3 to be 1. And that gives me my u2 is 1, 1, 1, 0. And c2 was 1 and c3 is 0, gives me 1, 0, 0, 1 for u3. Again, those choices are completely arbitrary. They're up to you. So your eigenvectors may look a little bit different than mine in a situation like this. Now you'll notice I have not included the arbitrary constant. It's implied. It's always there. Any constant multiple of these is a valid eigenvector. And if you take a look at them, you will see that they are linearly independent. It's pretty straightforward to check that. So what that means is then I have four eigenvectors. They're linearly independent, and they're four-dimensional. So I could use those as a coordinate system or as a basis for the four-dimensional vector space. And any vector in that 4D space could then be written as a linear combination of these four eigenvectors. It'll be clear in later sections why I'm even thinking in these terms of using eigenvectors as basis vectors.